Well, the next presentation is about external force tensioning, and it was supposed to be presented by Laco. Laco is a chartered bridge engineer with a broad range of technical and managerial experience. His technical expertise covers bridge and highway structures, design and assessment, and is profiled as an expert for post-tensioning systems design and durability.
Good afternoon, ladies and gentlemen. Welcome to the session concerning external post-tensioning. My name is Jan Laco, and I'll be giving the presentation on behalf of the authors. Strengthening comprising the installation of external post-tensioning to the existing concrete structure is going to be addressed. External post-tensioning can effectively increase structural performance, and it is easily inspectable with minimum requirements for future maintenance. External post-tensioning can be applied on various structures types, including box girder structures, eye girders, and slab structures. This method is particularly suitable for existing road bridges. These structures should be regularly inspected and assessed to ensure that the structural elements are adequate to resist increasing traffic load and structural deterioration over time. Once elements have been identified as having insufficient load carrying capacity, there is a requirement to either strengthen or replace the structure in order to maintain the safe operation of the road network. Where strengthening is required, the most appropriate form of strengthening will need to be assessed. External post-tensioning may be chosen as an appropriate method, particularly where deficiencies are found in existing post-tension structures. External post-tensioning can significantly increase the structural performance of a structure while minimizing further strengthening requirements. Strengthening by external post-tensioning is appropriate for various types of cross-section, including box girders and concrete composite structures. The method can be applied to strengthening midspan regions and both internal and end support areas. The critical cross-section stress state can be actively influenced by post-tensioning, which is its primary advantage over other strengthening methods where the structure is strengthened passively by attaching additional structural members to achieve higher resistance. Strengthening by external post-tensioning can introduce additional force which can increase the resistance of the section while reducing long-term deflections and crack widths where cracking has occurred. Using external post-tensioning can minimize crack widths or permanently close them, which is likely to improve the structure's durability. Complex pre-stressing systems comprise numerous elements required for the successful distribution of pre-stressing force into the structure. The elements required for external post-tensioning are high tensile strength steel strands of wires with 1770 or 1860 megapascal strength. Pre-stressing strands and wires can be either bare or greased and sheeted. Post-tensioning kits generally composed of plastic drum-fed anchorage steel block wedges and bearing plate, HDPE ducts, preferably smooth for external strengthening, injection material, which can be either cementitious grout, wax, or other flexible fillers, other elements such as anchorage caps, air vents, and deviators. All pre-stressing systems must have valid certificates, for example ETA. The pre-stressing equipment as well as the bursting steel reinforcement placed behind the anchors are also subject to certification. Pre-stressing tensile elements must conform to national standard, and it is generally recommended that low relaxation steel with up to 2.5% relaxation is used. Typical strand diameters are 12.7 or 13.2 millimeters, which is equivalent to 0.5 and 0.55 inch, and then 15.24 or 15.75 millimeter, which is equivalent to 0.6 or 0.62 inch. The strength can be individually protected by grease and plastic sheets depending on national requirements. Also, a wide range of other strength dimensions and arrangements are currently available on the market. Compacted strengths with a greater cross-sectional area utilizing standardized strength diameters can be used to achieve greater allowable pre-stressing force. It should however be noted that non-typical diameters and strength arrangements are rarely used for structural strengthening. We said that pre-stressing systems are complex systems comprising of various elements, and it is not permitted to mix particular elements from various suppliers. Therefore, for each job needs to be procured a specific post-tensioning system supplier, which then provides the system for the whole structure. And it is not permitted to mix various elements from various suppliers to achieve the results. And each pre-stressing system needs to be certified, and the certification is typically carried out for an entire pre-stressing system rather than individual standalone components. So components provided by one supplier but from various systems cannot be mixed, though all its parts have been individually certified. Let's talk about anchorages a bit. Anchorages can be either active or passive. An active anchorage allows stressing of the pre-stressing unit, whilst a passive anchorage allows only tendon anchoring without the option to stress, de-stress, or re-stress the tendon. Currently, anchors for 1 to 55 7-wire strengths are readily available worldwide, as well as anchorages for wire and rod systems. I said already, smooth surface HDPE ducts are predominantly utilized for external post-tensioning. The ducts used for PT should comply with national standards. Smooth HDPE ducts are usually produced in a factory and welded on site to achieve the required length. The polyethylene type should be either P80 or P100, and the nominal pressure class is chosen as follows, which is class PN4 for injection before tensioning of individual greased and sheeted strength tendons, class PN6.3 for injection at ambient temperature, and class PN10 for injection at temperature exceeding 16 degrees, which is suitable for wax injection. Pressure nominal class defines maximum allowable internal pressure in bars acting on the walls of the duct. The ducts need to be filled with protective material against corrosion, which can be either cement grout. Cement grout mixes must be certified and compliant with national standards. Suitability tests for grout properties, example given, volume stability, fluidity, and chemical composition should be carried out in accordance with relevant document and comply with national requirements. Or the ducts can be also filled with some kind of wax or grease, which depends on national requirements and regulations. And the wax must be compliant with the relevant standard for pre-stressing cable injection, and flexible fillers such as gels, thixotropic compounds, and other water blocking agents are currently available within the PT industry for cable injection. Now let's talk about pre-stressing equipment. All equipment and methods used for tendons installation, tensioning, and injection must be specified and carried out by certified post-tensioning suppliers. The stressing kits are generally defined by the certifying organization. The equipment required for pre-stressing installation is the following: welding machine for HDPE ducts, threading machine, which can be also called like strength pushing machine, jack and pump for tensioning operations, injection pump, and container for crude material. All equipment must be regularly controlled and maintained. Particular attention needs to be paid to jacks, which should be calibrated for all tensioning operations. Let's talk about stakeholders, its roles and qualifications. Let's start with owner. The structure's owner should provide all relevant available information from previous interventions, assessments, original design project, and construction records. And the owner may also specify additional requirements for service life of the strengthening elements, such as minimum or increased structural performance, durability of the strengthening elements, warranties, minimum disturbance of the structure service during interventions, and similar. The owner is also responsible for quality control measures, inspections, monitoring, and maintenance. The next stakeholder is the designer. The designer should be experienced in design assessment of post-tension concrete structures and bridges pre-stressed by external tendons. The designer should be able to carry out the structural analysis, which should adequately quantify the loading within the structure, which should then be compared to the calculated resistance of the structure, considering both the strengthened and the unstrengthened condition. The text says should, but basically this is a must. The design procedure is dependent on the existing condition of the structure, and therefore thorough inspection report must be available for the design. An understanding of the overall structural behavior is essential to carry out the design of the strengthening by external tendons. An important aspect of the overall strengthening is the design of attaching elements, such as anchorages of the tendons and tendons deviator, as these elements must be attached to the existing structure and therefore require particular attention to ensure that the existing structure is not overstressed or even damaged. Also key to the design is the development of a detailed construction sequence, as the addition of external tendons change stress state of the existing structure that may be well in excess of the compression resistance of the concrete. This is particularly of concern where the condition of any existing tensioning systems is unknown. In this case, it may be necessary to cut the existing tensioning systems during the staging of the works to ensure that the stresses within the structure can be controlled. The designer is responsible for delivering all agreed deliverables to the required quality within an agreed program and budget. The deliverables may include, but not be limited to, reports, design calculations, drawings, and strength elongation predictions. Let's speak about contractor. Only a contractor certified for post-tensioning installation work is allowed to carry out strengthening works utilizing external tendons. The anchoring and strength geometry deviating elements must be attached to existing structure, and therefore the work must be carried out with prudence. The contractor should provide all devices for the tendon installation as is responsible for their operability. The contractor is also responsible for the compliance of the materials used in the installation process regarding those proposed within the design specification. Prior to strengthening measures being proposed, an assessment of the structure must be carried out. The purpose of the assessment is to identify critical areas of the structure which should be subjected to strengthening. The design must consider both original and strengthened state of the structure. The assessment should consider future load prediction where it is possible to do so. Example given the allowance for flexible lane configurations on bridges. The assessment must be carried out in accordance with standards agreed with the owner. Strengthening by external post-tensioning tendons to be suitable for sections strained by excessive axial force, bending, and shear, and their interaction. Design standards require reliable service of the structure throughout its lifetime, and any proposed strengthening should therefore not detrimentally affect the service life of the strengthened structure. Where strengthening elements are not replaceable, the durability requirements are more onerous. The service life of non-replaceable structural elements must be at least the same as the remaining service life of the strengthened structure. The contractor must use materials and procedures which will ensure safe and reliable use of the structure over its remaining life. The contractor also provides deviating elements for external tendons which should be safely attached to the structure. These attaching elements must be robust enough to prevent significant deformation of both the original structure and the attachments, which could lead to pre-stressing force loss, lower structural performance, or damage to the structure. Some of the documents which may assist with external post-tensioning design are shown in this slide. Let's summarize the design assumptions. The bending effects introduced by external tendons should act in the opposite direction to the permanent and transient loads on the structure. The bending resistance of the section should therefore increase due to bending effects introduced by attached tendons. Secondly, the axial force introduced by additional external tendons can either increase or decrease the bending resistance of the section. The critical section should be verified as a section strained by axial force and coexistent bending moment. Thirdly, additional elements such as deviators and tendons anchorages should be attached to the structure without affecting the structural integrity, resistance, serviceability, and durability. Fourthly, all stages of the proposed construction sequence should be adequately assessed, as intermediate stages can have a significant detrimental effects on the structure. And last but not least, creep due to additional pre-stressing force should be calculated in order to its effect on bearings and expansion joints. Once it has been identified that strengthening of the structure is required and external post-tensioning has been chosen as the preferred option, the design of the strengthening elements should be carried out. The designer should bear in mind all the assumptions listed above. Another key factor is ensuring that adequate consideration is given to the difference in the tendon static behavior between bonded and unbonded tendons. The main difference in static analysis of external unbonded and internal bonded tendons is related to how the strain in tendons impact on the surrounding concrete structure. Bonded tendons assume full bond with concrete, and therefore the strains in tendons are matching strains in concrete in the fiber at tendon-concrete interface. The static behavior is different for external unbonded tendons, where in general cross-section the anchorage or coupler is not present. The tendons have different strains than those within the concrete structure they are attached to. The difference in static behavior is shown in the figure. The attached external tendons can be either straight or deviated. It is more difficult to construct deviated tendons, although they have more beneficial static behavior. In some cases, it may also be necessary to include deviators to avoid overstressing the concrete within parts of the structure. Another disadvantage for external tendons is the loss of eccentricity due to structure's deformation, where intermediate tendons deviators, reflecting the structure's deformed geometry in the midspan area, are not provided. To examine the loss of eccentricity, a geometric nonlinear analysis should be carried out. The resistance of the strengthened section can be derived from an axial force to bending moment, or so-called PM diagram, developed for particular section. In addition to this, when the structure being strengthened is an existing post-tension structure, careful consideration of the existing tendon condition needs to be made, particularly if an inspection has found deterioration of the existing strength. In these circumstances, the precise damage of the existing tendons is often unknown, and whilst it is common to design the new strengthening for the worst-case scenario, where a maximum number of tendons are damaged, it should also consider the best-case scenario where a minimum number of tendons are damaged to ensure that the new strengthening will not cause overstress within the existing structure. The installation of deviators and anchorage may also cause the temporary weakness of the structure while these elements are being connected. This temporary weakness should also be considered, particularly where it may have a significant impact on overall structural performance. Since there is a time limitation for the presentation to 20 minutes, I'll finish the presentation at this slide. Thanks to everyone for listening and to all co-authors for their contributions. The full text is available in Bulletin 103 Guide for Strengthening of Concrete Structures. Should you have any questions, please send them to jan.laco@dface.sk. And thank you again for listening and have a great rest of the day.
To conclude and close this webinar, I would like to address again my thanks to all speakers, to the remaining authors of this Bulletin 103, to all reviewers of the 12 chapters of this bulletin. There were several reviewers from all around the world, including members of the Commission 8 and Task Group 3.4. I also thank the FIB Secretariat, namely Corinne, for all her support. And I thank all attendees for being present and quite resilient, as Eduardo said before, until the end of this webinar. And last but not least, a very special thank you to Eduardo Cavaco that gave me great support, not only with the webinars, but also with the edition of these two bulletins. So you already know that they will be available at the FIB YouTube channel, so please check it a few days from now. I hope they will be there. So thank you very much to you all once again, and goodbye. See you in the next webinar.
Thank you.
Bye-bye.